Or speak French.
Or speak French. Well, we still know who you are.
Yeah.
Okay, so the recording is running. So thanks everybody for joining this virtual meeting. As I said, it's the last meeting before the deadline for our next voting virtual exceptional meeting. So if you have something, please send it in by Monday. We have three topics today. One is a quick thing on tools that Marc-André asked me to run by everybody. We have, in addition to the terms and conventions ticket to cover partition communication. This is kind of an effort to merge two concurrent tickets into one or into the standard. So Puri will lead that. And then afterwards, Ryan, you wanted to talk about next steps in partition communication, right? Ryan?
Correct. Sorry, I can't hit my unmute button.
Okay.
Yes, I do, but that'll probably be wrapped into some of the changes that we're going to discuss too. So
sounds good. Okay. And let's see how long we take for this. This may be a very short meeting. This may take all 2 hours. It won't get through. You know how those things work around here. So let me start with the ticket that Marc-André asked me to bring up. So you should all see my screen now, hopefully.
Yes, it's okay.
So this is part of ticket 168. This was a tools ticket that we already had in the forum, and we had discussions, and it was sent back to the working group, and we tried to simplify it. This is on the performance experiment session we have into the in-game PIT. This is not the sessions we were talking about normally. This is the idea. You can get a performance variable within a session. You should be able to measure this in isolation within your session. As another tool could create another session, do their own measurements, and then there shouldn't be any crosstalk between these sessions. That was kind of the idea. So we had in the initial text the sentence, any call executed in a session must not influence the results in another session. That was the intention, but of course that was not completely correct, because yes, you do influence it. If the other measurement is a timing, you will influence the timing. So there will be some crosstalk, you can't avoid that. But what we meant is if someone starts a performance experiment, it shouldn't start in another session. If you stop one, it shouldn't stop it in another session and things like that. And so that was flagged by Bill. I remember this right as it's passed through the standard. And we were asked to come up with an alternative to that second sentence here. And so after long debate, because the word influence is very, very problematic here because it can mean anything. But also as soon as you do something less, we don't cover anymore what we really want to cover. So we started to go explicit. So we now replaced it with the sentence, starting, stopping, reading, writing, or resetting a variable in one performance experiment session shall not influence whether the variable is started, stopped, read, written, or reset in another performance experiment session. It doesn't talk anymore that the value can't be influenced, because it can, but the semantics of the variable, the functionality of the variable can't be touched anymore. First of all, I know not everybody is fully in the tools topics. Did that make sense what I gave in context? And if so, does the sentence make sense, or are there any objections against that sentence? I hear quiet. Sign.
Good to me. Yeah.
Yeah, for me too.
Yeah, it's very explicit, so I think it really covers what you want to say here.
Right, that's kind of what we're going for. It's very explicit now of all the cases.
You know, my question really, what was the rationale for being so explicit?
Sorry, say it again, Pierre.
What was the reason for making it so explicit? I mean, literally, you have spelled out every combination there. So,
well, the thing is, otherwise you have to say somehow what is the connection between the two sessions, and that came always down to either being too constrictive or being too broad, where it's still the whole timing issue would still be an issue. So as soon as we went to the word influence, it became too broad and it didn't cover more. And so we thought the only way you can get around it is to be explicit and then list everything.
Okay, sounds good.
Okay, then I will give Marc-André that feedback that this was okay, at least with this group here. and then he will bring it forward for the meeting in August for I think there was an erratum, or I think it was an erratum, so we'll bring it back as an erratum to the discussion then. All right, thanks. That's what I had. So Puri, the rest is then the next step is actually you, I think.
Okay. All right, let me.
Do you need to stop sharing? I think so, right? Give you the ball. Oh, you have the ball. Perfect.
All right. To figure out how to get to. Oh, there you go. All right. So just a little bit of context. I hope everybody can hear me okay.
At least I can.
Okay, good.
Yeah.
All right. So some context. So as you all know that last meeting, the partition point-to-point communication chapter was essentially voted into the standard because it passed the second vote. So since the semantic terms ticket is, still, behind, we are trying to take the changes from the partition not the changes, I would say. We are, now that we have a new chapter, we are trying to make sure that the semantic terms chapter actually reflects what's been added in the partition point-to-point communication chapter. So we already looked at the sessions chapter, and that didn't have any impact on us directly. So there is not much we need to do. And there was, of course, another function that was added, the non-blocking send and the non-blocking send receive function and the send receive replace function. So we handled that. So the only thing that was pending, which we had to consider as part of the semantic terms, was the partition point-to-point communication chapter. And again, since we are doing the semantic terms later, I think this time around we are taking the responsibility of incorporating any changes to this particular section. Going forward, assuming that this particular semantic terms ticket is voted in and accepted into the standard, then whoever else proposes a new functionality, they have to make sure that it fits with the semantic terms and then the corresponding table in the appendix. Okay, so working with the partitioned communication point-to-point communication chapter, we reviewed the terms that are currently defined, and then how do they match with the terms that are defined in the partition point-to-point communication chapter. So based on that, we had to make one, of course, we have to update our table. So I will come to the table at the end. Before updating the table, we had to also clarify a couple of things in the semantic term section, and that's what I'm going to show next. Okay. So the text which is in black and outside the box is what we currently have. So we have a persistent definition of a persistent operation. So it is defined as for a persistent operation, there is a separate procedure for each of the 4 stages as shown in the figure and defined in section. Each of these procedures may be blocking or non-blocking. So with the inclusion of the partition communication chapter, we would like to add 2 sentences after this. Okay, so the rest of the section is not going to change. It's just the addition of these 2 sentences. And I'll read out that sentence, 2 sentences. For a persistent operation of a partition send, an additional call to activate each partition of the send buffer C section 4.2.1 is required to finish the starting stage. For a persistent operation of a partition receive, the user is allowed to read part of the output buffer after checking for partial arrival of the data before the operation is complete, C section 4.2.2. So just to give some context in terms of why we need to make this addition is because if you have followed through the discussion of partition communication, it's a different type of communication. Traditionally, we have these 4 calls and basically 2 stages, inactive and active. However, in the partitioned communication, the starting itself, if you just call MPI start, it's not really going to start the communication. You have to indicate that a part of the buffer or a partition is ready to send through a separate called p-ready. Okay, so essentially you need MPI start and a bunch of p-ready to do the starting. Again, starting is defined as handing over the control of the buffer to the MPI, and the user no longer going to modify the contents of that buffer. Okay, so based on that definition, okay, so the starting stage would require not only just calling the start function, but also calling the p-ready function. That's what the first sentence is trying to capture. And this corresponding second sentence talks about the receive side. So on the receive side, okay, so there is no p-ready, but there is a p-arrived call, which basically checks, hey, is the buffer ready for me to reuse? Okay, and again, it's not the complete buffer, it's the partial buffer. So the second part of the sentence says that, again, for the receive operation, the partition received operation, typically we say once once something is complete, then you can access the buffer. So again, we are having partial completion because this is partition. So you can have access to a part of the buffer or a partition without the call completing. So again, each of these calls have a request object. So the request hasn't completed, but a part of the request has completed. So that's what it is referred to as the partial completion. So that's what we are trying to cover with these two sentences. And obviously, you need to go read that chapter if you're not familiar with partition communication to understand this. But that's what we have highlighted here. Okay, so this is the change that we would like to make as a no vote for the next meeting, so that we could cover changes, cover the introduction of the new chapter, which again introduces a new concept. Unlike other API additions, which are based on existing concepts, since this chapter introduces a new concept of partial completion and partial start, we have to add this text to indicate that. Okay, so I will stop here for now and let everybody digest this a little bit and ask me any questions, and let Ryan chime in to see if I'm missing any key points here, as well as other members of the semantics terms working group and the persistent partition working group.
Puri, thanks. I just wanted to mention to people that obviously partition communication has worked closely with semantics terms to write this text, so it's not like this is the first time I'm seeing it at all. Just as a note, the first sentence is absolutely key because it tells you what you have to require. You're required to do stuff to move into the final completed state. The partitioned received, just to remind people, you're not required to do any of that. If you want to, you can pull for partial arrival of data, but it's not actually required to move it towards completing in any way. You don't actually have to p-arrive every single partition before the operation can complete. So there's a requirement in the first sentence that you actually have to call p-ready before you can actually move into a completed state for the request as a whole. But the partitioned read, you don't have to, the receive side, you don't have to do any of that stuff if you don't want to.
Again, the reason we emphasize that is to let the user know that, because typically we say that you cannot access the buffer until the operation has completed. So in this case, you're able to access part of the buffer even before the real request is complete. So that's the distinction that we wanted to make sure that people get it here. But obviously, you need to read the rest of the chapter to know the nuances.
So as we discussed in the working group, this will also require some changes to the actual partition ticket. Have you thought about that?
Ryan will talk about that hopefully after this. So I didn't, go into those topics in this particular presentation.
Okay. Just so that people know, in case they're curious and want to participate in the discussion, the issue is with whether we say the user is allowed to read part of the output buffer or whether they're more broadly allowed to access it and how they're allowed to use that entire buffer. The language in the chapter simply says access. It was meant as read, but this has also led me to think a little bit more about what we do and do not want to allow to happen on that buffer. It has some ramifications for operations on accelerators. So we'll have a little bit longer discussion about this in the working group to make sure that's exactly the word that we want to use. But if you're interested in having those discussions, it will become more clear after I give my presentation later on GPU stuff. Why we would care and what we want to do there exactly. But as it was intended in red when we originally wrote the text.
So this is the one thing, and the other thing is when is the starting stage finished, right? When is it started? I think the texts were not consistent there. At least that's what was my impression of reading it. I know if you had I haven't checked my email most of the day because I was out.
Right.
But did you come to a conclusion on that?
Yeah, so, at least, Julian and I, suggested a couple of changes to Ryan. And, Ryan is 1 hour behind us in his time zone. So probably, he's just catching up with his email. So once he's caught up on his email, he may be able to review that and respond to those changes. But, we did, at least Julian and I did point out a couple of things to Ryan in terms of how the text in the partitioned communication chapter needs to be updated. So again, I am presenting this from the semantic terms, working group perspective. Obviously, there needs to some changes happen in the text that has been accepted, and to make it consistent based on the definition. So again, starting. Typically we have been using, the MPI start all is what starts, but in the case and that is not sufficient. You need to do start all and a series of p-ready to finish the starting stage. So those things need to be spelled out explicitly. There may be a little bit of overloading there. It may be saying starting just to refer to the MPI start call, not start plus p-ready. So those things need to be still updated or clarified in the partition communication chapter. So that I'm not, discussing with respect to this particular ticket.
No, I think that makes sense.
Yeah.
I mean, for everybody, I mean, we had this discussion in the working group already, and this is still a bit ongoing. But this is a typical problem of merging two major tickets into the standard, right? And so if there need to be changes to the partition communication, I think we decided the plan was to bring this forward as an erratum to make sure we can get the tickets in sync in time for 4.0, right?
Yeah, that's the current plan. So that way, the terminology is consistent. So we have, basically two things going on at the same time. They have tried to do their best. They are using the same, phrases, starting, initialization, completion, freeing. They are using all the correct keywords. It's just that, because partitioned is a little different, they are using the word starting, which really, according to the definition, basically, so far has been just MPI start. But now it is start plus a bunch of p-ready calls. So they need to update the text to do that, show that judge.
I have a question about the first sentence.
Uh-huh.
I'm a bit puzzled by the first part of the sentence. So my understanding is that a partition send is a persistent operation.
Mm-hmm.
But the sentence says for a persistent operation of a partition send. So what is the persistent operation of a partition send? I'm trying to understand the wording, if that's really what you want to say. Shouldn't it be wouldn't it be enough to just say for a partition send, because the partition, or for a partition send operation, because that is already persistent.
So let me see what was the rationale for that. Martin, Julian, Ryan, do you all remember what is the reason we added this particular for a persistent operation instead of just saying for a partition send?
There may be in the future versions of partition sends that are not persistent. So the idea here was this particular operation of procedure language was a semantics terms thing that I don't entirely get, but it's a persistent operation, and then the procedure implementing it is the partition send set of procedures, right? I agree the language is a little awkward. Maybe we can figure out a better way to say it, but that was sort of the idea there, was that it's a partition send of persistent operation type.
Okay, but now it's just the other way around. It's a persistent operation of partition send. Right. So
Yeah, maybe it should
the arrow is in the wrong direction if you think about it as a diagram.
Okay, so I see what you're saying. So
maybe what we want to say is for persistent partition send operation.
Yes.
I think the partition send operation is used in the partition chapter. So maybe what we want to say is for persistent partition send operation.
Actually, now thinking about this, is I know that was the reason why we did this way, but is the persistent really critical here? Because if you have a non-persistent, you have the same thing. You need to call for each partition before you get into the end of the starting stage. Even if you do like an IP send, right? That would be still the same thing.
Yeah, I think that we wanted to convey the persistent, the fact that it's a persistent operation. That's why we wanted to.
Right. So we wanted to highlight the fact that the partition send is a persistent operation. But I guess it's kind of redundant since we are.
So I guess the question is there right now, is a partition send only a persistent operation? Is there a notion of partition send that is not persistent?
Not right now.
So yeah, so maybe it's redundant.
Yeah.
But I think that what we wanted to do is to be feature proof. That if in the future you have another version that is not persistent, maybe it is covered already with this text. Right now, it seems redundant, but maybe in the future it's not going to be the case. So
we've specifically had requests to originally in the ticket there was a p-send, like an ip-send. It was a non-blocking p-send that was not a persistent type. So we took that out because of forum. But the intent was always to add it back in later. It was just leading to too many side discussions with too many variables at the same time. So our intention is to add it in later.
Okay, but
I agree. So it might be helpful to not have to revise this text, but if we want to revise it now to just say the general thing that's in 4.0, we can always revise it in the future when we introduce the new type to make the semantics terms section correct for new types of partition communication.
But so even then, it wouldn't be future-proof right now because the first part of the sentence clearly limits it to the persistent operation.
Right.
So the way it's phrased right now, it's not future-proof.
So I think probably what we wanted to say was for a persistent partition send operation.
Yes.
I think that would have at least.
Yeah.
And if you leave out the persistent, then it's future-proof because then it doesn't matter if it's persistent or not.
Right.
Right. That's kind of what I'm going for too, because the activation of each partition is the partition part, and it doesn't really matter if that's a characteristics of the partition, not of the persistent, right?
So for whatever reason, I'm not able to edit this right now. Has anybody got a lock on this?
No, actually, I tried that too, and it didn't work for me either. I don't know why that is. I thought you had it locked.
I'm the owner, so I don't know what's going on here. It's not letting me tell it. Oh, so at least let me make a note here. Maybe it will allow me to. No, I can't do anything. Okay, I can at least type a note here. Let me see. Oh, this is monk text. Okay. Hold on. So we want to say something like for a partitioned send. We don't want to even say persistent operation. So we want to say for a partitioned send operation. Is that the consensus?
I think that's correct.
And we need to do the same thing for a partitioned receive operation. Okay, so you basically get rid of the persistent part there. Does that make sense?
Fine, this doesn't bite itself with any of the ideas you have going forward here, right? This is still correct.
Don't think so. I mean, let's put it this way. Making it more general doesn't necessarily hurt us, I don't think. I wasn't really upset with the persistent operation version in terms of the fact that it is true, it just might become more broadly applicable. So I think either one probably works for us. It's just whether or not we need to edit the text again in the future. So the newer version that's more general, we won't need to edit the text as often.
Okay,
Okay.
there is something that I don't get here. So
Okay.
A persistent operation is a separate procedure for each of the 4 stages. So we have initialization, starting, completion, freeing, right? That's the characteristic of a persistent operation.
Yes.
So right now we have for the partition send, there is only a persistent version, right? Okay,
Right.
so it's what okay, so it's what I am okay. In the future, there will be maybe a partition send that is not a persistent operation, but if will this partition send this partitioned send but not persistent operation be composed of still of 4 stages?
Yes.
So right now we think so.
That's weird. So that's weird. That's where I'm lost. Okay. So if we say that a persistent operation is composed of 4 stages, and we say in the future we're going to have a partition send which is not persistent but also composed of 4 stages, it's a little bit, well, I'm lost.
So it could be more than 4 stages because it could have all these sub stages. That's the.
Yeah. I mean, blocking and non-blocking are also composed of 4 stages.
4 stages, right?
They are, most of them are combined in one procedure.
Okay, but it's okay. Here, okay, it's not the 4 stages. It's the fact that they are in separate. There is a separate procedure for each of the stage. Okay, that's
in the persistent case, yes. But if you just had a non-blocking version of partition, then there wouldn't be 4 different stages. They would be combined into 2 procedures, right? Instead of 4.
Yeah.
What happened?
Getting some background noise here. Okay, so are we okay with saying a partition send operation? Do we really still need to say partition persistent send operation?
I don't think we need the persistent because we are in the persistent operation definition.
Okay.
So
all right
now, where it's put in the text, it only relates to persistent operation.
All right, I'm good with that then. So once I figure out how I can edit this, I can put notes but not change this. So I don't know what's going on.
That's strange.
You're still presenting it somewhere in another window because it won't let you modify stuff while you're presenting it. Maybe that's the problem.
Okay, that could be it because I had it under. Okay, hold on. Just do one thing. Let me do the stop sharing. Go back and then. No, apparently that didn't. I thought I had a separate presentation window, but looks like it's not. Okay, let me do the sharing back again.
Not a big issue. If afterwards we can just, download it as a PowerPoint and modify it there if you want.
Okay, and also instead of the power, I tried to do the whole screen share, so hopefully that would change things, but it did not. Okay, all right. Now let me get back to the presentation mode then. All right, so I guess I have this pointer thingy. Ooh, that's it. Okay. It's making streaks. All right, so once I make that change, so instead of saying for a persistent operation of a partition send, so if we say for a partition send operation, and same thing for a partition receive operation. Okay, so any other concerns, questions?
Guillaume, does our answers help you with, or
Okay,
you are still the same problem right now?
No, I mean, you probably followed the discussion more than I did, so I don't want to crash your party here. But I'm buying the fact that this paragraph is part of the persistent operation. So removing the word persistent makes sense to me. Okay.
Yeah, I agree with that. Yeah,
I fully agree with that. It's not an issue for me. If you remove the words, okay, go ahead. It's to me it's clear. But I'm just wondering, what if in the future? And okay, but maybe it's too early to. Okay, so
I think so. From the discussion right now, I think we are pretty convinced that the persistent semantics covers the partitioned, and that right now it's really we don't need more stages or.
Yeah. So completely. I agree with that. So yeah.
But you are maybe in the future we'll see. Okay, we really need another thing, but so far it fits.
Yes.
So let's try to do it at least for 4.0 and see what's coming.
Okay. Yeah. I agree with that.
Okay. All right. Thanks, Julian, for confirming it, Graham. So that way, we can, again, we can talk more too. So if you need to.
If this changes due to partition communication additions or changes in the future, we'll make sure that we come back and move around this semantics text so that in future versions like 4.1, it is correct and consistent. But I think for 4.0, this is the minimum change for a no vote to at least get it covered on this version. And we'll revisit this if we make further changes to partition communication in the future.
Yeah. And I think that's the important point that, we are really trying to accomplish. So we could have initially said, okay, we don't want to touch that chapter, forget it. But then we said, okay, we are adding a brand new chapter, which is actually introducing new semantics. And if we don't explain to the user what it is, then, that would be a bad thing. So that's the reason why we decided to add this as an, additional change and go through the no vote process. Yeah, so in the future, whoever adds new things, they have to take care of this. So for now, the semantics terms group is doing it. Yeah. All right. Now I think many of these questions probably will get answered in the next slide, which has this table. So we will have additional entries into our table in the appendix. So again, this time around, we are doing it, and in the future, whoever adds a new API, it's their responsibility. So since, we promised that we will keep this table up to date, at least as far as this current ticket is concerned, I know that, Catherine had a concern that we are adding this table and, how are we going to keep it current? So for now, we have taken the responsibility, but in the future, whoever adds a new API, it would be their responsibility. So we are going to add 2 entries. Sorry, I need to get rid of this thing. Okay.
So right now, when someone wants to introduce, a ticket or a new pull request, you have to check all these boxes, that you did the index, etc. So maybe Wesley can add another box. You have to tick the box. I did the update to the table in the embeddings.
That's correct. So we have already added a checkbox for the semantic terms, but another checkbox needs to go for the table.
Yeah, that's a good idea. I'll bring that with Wesley.
Okay. All right. Thank you. So the two so we have to again make 2 separate set of boxes, if you want to call them. Initially, of course, we just had it as one set of boxes, but then Rolf recommended that we break that into 2. So we have one for the send side and one for the receive side, basically. So we have the send init, start, then the p-ready, wait, and then the test, and then the request free. And then the corresponding stages and whether it's completing or incompleting, whether it's local or non-local, whether it's a blocking or a non-blocking operation, and then what type of operation. So we introduced it as PP to avoid the confusion with the partition. We said persistent partition. So we said PP as a new label for those. Okay. And so I think this is the reason why we added that qualifier in the beginning in the previous slide, but I guess now it's kind of obvious why we did that. And then of comments that go with that. So by the way, notice that the p-ready appears only on the send side, and of course it is required, whereas on the receive side we don't need it. There is no p-ready, it's only p-arrived. And since it's got the semantics similar to the test where you have a true and false, so we have to separate out the 2 cases, true and false. And we added obviously the earlier, so the footnotes 7, 9, and 14 were there before, so we didn't change them. So we added 2 additional footnotes, one for the send side and one for the receive side. So basically the footnote on the send side it's essentially to clarify that start is not sufficient. To complete the starting stage, you have to do start and then a series of p-ready to complete the starting stage. And similarly on the receive side, while typically you won't be able to access the buffer until the operation is complete. Since p-arrived allows you to check for partial completion, you could use that to determine if a particular partition is complete and then access that particular partition. So again, access here is read. So we did explicitly say read part of that partition, because typically completion, before the request is complete, you can't touch the buffer. Here we are saying that this is an exception. So that's what we are noted that with the footnote 21. Okay, and of course that happens only when it's true. When it's false, it doesn't matter. Okay. And again, which stage are all these functions being in is marked as well. Any questions on this?
Quick question, because I don't remember it anymore. A MPI test, a regular MPI test that returns true. Did we also mark this as non-blocking? Because it kind of requires a function on the other side to turn it true, right? It's a matter of how you interpret it. This is consistent, basically, what I'm asking.
Yeah. So basically, I copied the persistent point-to-point, and then modified it. So whatever happens in the point-to-point is what's happening here also with respect to test.
But in the corresponding test, we don't have the non-blocking marked.
Which particular line are you talking about, Martin?
The second and third line from the bottom in the receive part.
Uh-huh.
There's no information in the blocking column.
Oh, you mean, okay,
No,
why we
no,
left them? Uh-huh. This is what we did with the other cases too.
Then I'm wondering if it should make something in the because a P arrived is not for that partition is like a test, right?
Yeah.
Yeah. Oh, so you're saying why we explicitly made
Say it here, not on the other one, yeah. That's why I was asking how it is in the other tests.
I see, I see. Yeah, so in the other cases, it's just like this, empty.
Then I would leave it empty too, just as a first inkling. It's the same thing, right?
Right. And I think from that perspective, it is not required. Again, test is not really required, but as long as you do either wait or test, okay. So maybe you're suggesting that we should try to keep it similar to the test here and not say explicitly whether it's blocking or non-blocking rather. Okay.
Sounds
All
fair.
right. Yeah. So I need to cross that out. Okay. Okay, I thought I had the annotate somewhere here. Okay. Okay, all right. I'm going to just scratch that out, scratch that out. Okay. So this would add the two new footnotes to clarify the partial completion and partial starts.
Yeah, you would have to remove the footnote 14 from that line too, right?
That's true. Well, that is because this is still I,
But we're not making any conclusive say whether this is a non-blocking procedure.
Yes. If you don't, so you want it to be identical to tests. Okay.
I don't know, that's my gut feeling. I don't know if anybody else has any strong opinions here, one way or the other.
Yeah. I think it should match with test. I agree with you. So if we didn't do it for test, then why are we doing it for PRI?
Yeah, we wanted to over-specify, but we should keep it as the same as test.
All right. Any other questions, comments, concerns? If there are, that's all I had. So if there are no questions related to this, so this is what we were planning to bring in as a no vote, the addition of these entries into the table and the text, addition of that text. So
another usual question, of course, is there any objections? Anybody who has headaches over this, if that will be introduced as part of a no, this case is not really intended to change the ticket, but just to adjust it to make sure it stays in sync with the standard.
we could have basically punted this off and said, hey, this is not part of our ticket. This is part of, the persistent, the partition group. They should go back and do it. But unfortunately, this wasn't already done when they when they did this. So if we had gotten first, then of course the onus would have been on them. So since we were behind, we are taking the responsibility of updating it. But of course, in the future, whoever adds a new function, it's their responsibility.
This is kind of a unique situation where, stuff was going on in parallel and you can't put in pull requests on other existing tickets. I mean, otherwise, if you were writing an existing ticket, you'd have to take into account every single other ticket that's currently being written and make sure that everything was updated in them as well. I don't know how we do that in the future.
Yeah.
So
even now, right. Yeah, even now, I think I have an issue with this because, Brian was waiting for some of these changes to commit to the, to merge with the 4X branch. So Bill is actually waiting on those changes from Brian. So until that happens, I can't even reference these functions, right? Because I will be, referencing sections which don't exist in the branch that I have. So this is a challenge.
Yeah, that'll be done soon, Puri. We have one member off on vacation who we want to get to sign off on something, but I think we're done at this point. So,
right. That's why I'm not.
Agreed. All this stuff sort of happens all at once when we're modifying parts that interact with each other.
Yeah, and the problem is also we are so close to releasing the new standard that we have to pack it all together in a really short amount of time.
I've got a question, Puri. I'm sorry.
Sure, no problem.
For the collective nature of the operations, there is a dash except for P ready and P arrived. Why is that?
Under the collective?
Yeah, yes, exactly.
Oh, okay. I think that's just a copy paste error. Somehow that column didn't get copied. Oh, I know why, because those were the new lines that were introduced and that didn't have a dash. So those lines need a dash. So they should be exactly like the other. So it's not any different.
Okay.
Yeah, thanks for pointing that out. Yes, that's definitely an oversight. Yeah, that's a good catch. Yeah, there should not be any reason why it should be any different than the others. But by looking at that, these are all the new lines I have added. So all the new lines that I have added looks like I did not put a dash in that particular column.
I've highlighted all this stuff on the original Google Sheet presentation.
Oh, great.
So
okay, great.
It's all highlighted. We'll make sure that those changes get made.
Oh, thank you for doing that, because I would have ideally just showed that, but I thought this would be better. So thank you. Okay, thanks, Guillaume. So anything else? All right, if there's nothing else, then I'm going to stop my screen share and hand it over to Ryan. I guess hand it back to Martin. So I'm assuming Martin will.
Just a question again. So is anybody have any worries about this and would and has any concerns for this when this will come up for vote? I think that's what you want to know, Puri, right?
Yes, yeah, absolutely. Would anybody, vote this down? No. So, then we'll basically go without this, reference to partitioned communication in the semantic term. So if people want that, then that's up to them. But, is anybody have any concerns that they don't want to make this change?
So we'll take this as an overwhelming yes.
I guess.
Okay, thanks, Puri.
Yeah, thank you.
Sorry?
I said thanks, sorry.
No worries. With that, let's go to Ryan on the partition, on the forward-looking stuff in partition.
Okay, that just let me take over presenter, so I will start sharing now. Hold on one sec. Okay, can people see slides?
Yes.
Okay, perfect.
Yep.
I'm just going to leave it in this mode for a little bit. because I anticipate I'm going to be making notes and changes on these slides as we go through. So partition communication, remind everybody it's voted into the standard as it is right now. We've been aware for a while that partition communication was obviously originally designed for highly multi-threaded environments. There are some elements there's one element of partition communication that could be really optimized for GPUs that we didn't understand enough about the performance ramifications and how good it would be to optimize for it until after the ticket had been voted on. So we punted this to 4.1 with the hopes that we could have some good optimization for GPU accelerators in particular that to support them. So here's sort of what we've been thinking with partition communication and sort of present the problems that why we think we could do a good job of introducing one extra call to make a huge amount of optimization for GPU, and how this whole using partition communication with GPUs paradigm would work with regards to where communication setup and actual communication initialization happens versus when it's triggered, and how we think this would work really well with GPU environment to be able to enable MPI type communications on GPU without a full MPI library on the GPU. So the goal here is that partition communication is really aimed at multi-threaded, multi-core devices, of which you could argue GPUs definitely are. But a lot of this requires some basic capabilities in things that GPUs are not necessarily great at. So we want to apply these same principles in a slightly stricter environment to avoid operations that GPUs and other data-centric accelerators are not good at. So things we want to avoid here, if you're not familiar with GPUs, we really don't want to put in extra if statements if we don't have to. We want to avoid things like pointer chasing, of which, MPI requests objects are not necessarily awesome. We want to avoid, if we can, lots of software progress of MPI in the accelerator kernels themselves once you've launched a kernel. And we'd like to avoid operations that require commands to the NIC to be created on the GPU. So let me step back here for a second. This is outside of MPI, right? This is the really low level stuff that you need to do. Underneath MPI, when you get down into the device level drivers for what it's doing to actually communicate to the device, you end up basically writing a set of commands out to NIC hardware. Those NIC hardwares take in their command queues certain coded variables like you would in an operation for a CPU, and all of the associated information that you need, like address, the length of the buffer, the destination that it's going to, potentially the destination buffer address locally at the other side, and a whole bunch of other information that you need to write out to this command queue. A lot of this stuff you already know ahead of time in partition communication, right? So the destination buffer, this sort of stuff you probably already know ahead of time, and so you don't actually need to write all of that stuff out. You can probably set the command entirely up with partition communication and literally just say, okay, when the partition is ready, set this command in the command queue to active and it'll fire off. So we'd like that type of solution. So we want to avoid writing that entire operation, assembling it and pulling it together from multiple different places and writing it all out to the NIC command queue at once. Doing that sort of IOVEC type gather to create a command and send it out, the GPUs aren't particularly awesome at. What we do want in these cases are we want the buffer to be ready to send receive as soon as the kernel launches. So truly in partition fashion, the data in the buffer is not ready yet, but everything else is done for you, right? And we want very limited interaction with the network. So when you call that ready call, unlike on, for example, a multi-core CPU, you can get some extra performance benefits from using partition communication the way it's used today. So by lazily registering the fact that the buffer on the other side might not be ready, some of my partitions are, and I want to gather them together and I want to optimize them. I want to pack them together in good sized chunks to send over to the other side. I want to do a lot of stuff potentially with the buffers. Those cores are particularly good at doing those sort of operations. And so there's benefit there. We can do a whole bunch of extra overlap and potentially get some extra performance out of our network. At the GPU level, the GPU is not good at doing that. So any benefit of doing those particular type of operations may not be super beneficial at a GPU side. But doing something really, really lightweight from the GPU to just trigger things that have been set up on the CPU can be beneficial. So this is sort of what we want in a GPU solution. And we're very, very close to that in our model. We're lacking one particular call, and I will get to that in a second, that will help us guarantee that one particular path for the partitioned ready call is always taken, versus what we have now, which is you could have potentially multiple paths when you call preready taken that give you extra optimization opportunities. For a GPU, the optimization opportunity is eliminating all those other optimization possibilities and just doing one thing the same every single time. Okay, any questions about this? I should mention that this is done in combination with talking with vendors and the system integrators and everybody from AMD and NVIDIA who produce these devices. So this is what they're telling us that we need for the best performance on these devices, and this is what we're trying to get out of these. Okay, I will remind you of these things as we go through the next section. So what have we been discussing in the working group for partition communication? With the participation of our accelerator vendors and the working group, we looked at basically two different models that you might want to use on the GPU for communications. Kernel level communications, which is, think about that as you run a block of code on a GPU and it returns. Streams are more fine-grained than this and more fluid. I'm not going to talk about GPU stream level communications today, and the reason for that is the kernel level triggering and device communication is what we're hearing, at least from our app developers, as the most desirable mechanism. They know how they would do this today with partition communication. They understand how they'd structure their communications. There's no debate on how these things get set up. Streams, for instance, we're even having changes at the hardware levels, and the hardware designers, whether you have streams or whether you have graphs, it's not entirely set yet. So we're just going to set that aside for a second. We think these same approaches will still work at the stream level, but because that's not as settled and cohesive a mechanism between all of the vendors, we don't necessarily think that we should go there yet. And so we're just going to talk about communication on the level of a kernel starts, it completes, we want to do a communication within that kernel. So a whole bunch of these discussions arose around the ticket. While the ticket was in voting, we opted to work on this as different ticket follow-up. And our target here is MPI 4.1. So this is probably our first 4.1 discussion that we're having. What we'd like to do, though, is get this discussed and moving forward as soon as possible, because we'd like to be able to tell our applications teams that want to program with GPUs and do some MPI communication from them, whether or not something like this is available to them as a tool in MPI, as in quote unquote being in quote unquote the standard. Whether or not that standard is published or not does a lot to help the adoption and the comfort of our app developers working on these things. So we wanted to follow this up as soon as possible. Any questions about that? Okay, great. So this is the general usage model expressed in code, so we can maybe have a little easier discussion of this. So the idea is that on your host CPU side, you've done a partitioned send init. So you've initialized something once, and then potentially you're going to do a for loop. You don't have to do these multiple times, but I'll show it as a persistent operation for you. So you do an MPI start with a request, then you're going to launch this kernel, and you're going to pass in some information to that kernel about the partition / the request for it. So you can launch this kernel, and it starts happily going along on GPU. In some way, we identify our partition through our ID on the GPU device itself. So there's some way that we can identify individual partitions for GPU thread blocks or individual threads even, how you can assign them IDs for writing out to their portion of the communication buffer. And then you're going to do a whole bunch of compute somehow, whatever you're doing to actually fill that buffer with the data you want to communicate. And then you're going to do an MPIP ready when you're basically done with it, so that we can trigger that communication to happen. What's probably actually going to happen here is that the CPU, because the CPU's already done the setup and completion, the setup for all of this communication, what's actually going to happen is the GPU can potentially just push out a small notification, basically ring a doorbell. There's a variety of different ways that you can do this on hardware today. There are doorbells straight on the command queues. You can do things like increment counters that exist. If you needed a software solution for this, it would actually be a small ping back to the CPU, which would then initiate the request on the NIC. There are a variety of different ways that you could do this, but it's very lightweight because you know that everything's ready and you just fire it off. And then when the kernel completes, right, our communication has already had the opportunity to occur and may already be occurring. We complete our kernel and we do our MPI wait. Everybody at this point is called MPIP ready at some point for each partition because you hopefully coded it correctly in your GPU kernel. And your wait now just sort of finalizes the request. You need to finish any of your communication. You start up again with a 4, you're doing a start, and we launch it on the kernel again because all of our communication was reset up from the CPU side. We've programmed that NIC with those commands before we launched the kernel. Now, the problem with this is that as it exists right now, let me get to this next slide. GPUs are not really great at a lot of the previously mentioned operations. So a lot of the optimizations that exist on certain devices are not necessarily good optimization opportunities on a GPU. What you really want on a GPU is when you launch that kernel, your buffers are done. You know that your remote buffer is ready to receive your data, and so you don't have to make any decisions. It's literally changes that P ready from, is the buffer not set up? If that, I might want to make a decision about holding it back. Has the buffer been set up since I have previously had things held back? Okay, then I'll aggregate things together and send them over in a smart way. In the past, you might make a decision of, do I want to aggregate certain partitions together to make better use of my network? We don't want to do any of that stuff. We want the one path that exists that comes through that just says, buffer's set up and I'm not going to do anything. I'm just going to send the partition that you told me was ready. I'm just going to send it. I'm not going to try to do anything fancy with it. On the GPU, reducing all of those ifs down to that one case, the case where the remote buffer is ready, and I know it is, and I can just send exactly what you told me was ready, is the most optimized path, the most desirable path. So we're not trying to leverage extra overlap time. We're not trying to do anything smart with aggregation, using our network and our MTUs more efficiently. We're going to throw all that stuff out the window for the sake of really easy to implement P-ready with no ifs, just simple ring a doorbell. But the problem with this is we don't have an efficient mechanism to guarantee that the buffer is actually set up before you run these GPU kernels. Calling MPI start does not, because it's a local operation, does not guarantee that the remote side's buffer is actually available to write to. So this is the problem, that it then creates, the GPU still has to do the if, right? It's got an if of 2 ways. If the remote buffer is not ready, okay, I got to do some stuff. I got to add things to a list of things to send. And then you still have the if of, am I the first one that realizes that the remote buffer is now clear to send to, and I have to send the backlog of everything that was ready that didn't get sent because the buffer wasn't available. And then the third path of the buffer is available and I'll just send whatever. So it still leads us to this if. It's okay, but it's really not as efficient as it could be. This optimization is apparently going to be much more efficient on GPUs from our initial observations. So any comments about this? This is sort of the problem that we're trying to solve, the model for computation that seems to be the most effective, that application developers want to use for their GPU communications. And we can support all of this in MPI today. This is just optimizing it. So any questions?
So this makes the fundamental assumption that the kernel on the GPU is part of the process that launched the kernel, right? The API process, at least. Did I see this right?
Sure, if you have to make that sort of
Back to the previous slide, Ryan, if you don't mind. Thank you.
yeah, I'm assuming that the kernel launch is launching from the MPI process. Yes, that is the model.
Right, and it becomes all threads spawned on the GPU, or launched on the GPU, become part of the same process, right? Or are part of the same process.
Sure, you could view it that way. Yes.
This is a political statement more than a technical statement, right? Just go ahead.
I guess so, yeah. I mean, it has implications on what we consider an MPI process at the end in the terms, right?
We thought about this too. Essentially, it's no different from our mind than if there's a vector instruction called inside the compiler, right? Our view is that it's just part of the entirety of what a process can do with resources it has on that architecture. So yes, I would accept that it's part of for the purposes of an MPI process, it's part of the MPI process.
You could, you can come down on each side of the theoretical argument, but you could regard a kernel as essentially like a fork, right? That just happens to happen on a different device.
Well, there will be some limitation because you can't call everything there, right? You can only call some parts.
True.
It's no different than saying that there are restricted thread contexts in a tools chapter, for instance.
I guess so, yeah. Okay, that was more like a clarification statement. I think that would. I think the
I knew it was coming, Martin. That's why I've been waiting for this question. It's a very deep question. What is a process in the context of when there's many things beyond our understanding of just a single threaded CPU anymore? And it's much more complicated moving forward. We try to say the least we can, but eventually we may have to.
I mean, the thing is, if you think about doing this from an FPGA, you may want to do the same thing there, right? And have the ability to call ready from an FPGA.
We're doing this exercise actually literally in one of our projects. And so we're tracking both the FPGA and GPU version of this story in the group. We're planning to do those in parallel, part of the pun. In concert, I'll say, to be careful, so that we get all the major GPU vendors, and we also have an idea of how it works when there's an FPGA in lieu of a GPU to get the same programming model to function. So we are considering that use case as well. We think it will be analogous to what Ryan is saying here, although an FPGA might be able to do more of the things that are hard for certain vendor GPUs right now. So it's going to be part of the gatekeeping and actual prototyping research that we do outside the forum.
Oh, cool.
Yes, other accelerators may not have these same issues, but it may be very useful, especially for like FPGA situations where you may choose to make something way more complicated that you don't have to guarantee that the buffer is available. But for more simple FPGA models, you might just, this is a lot simpler for you. So it depends. But yeah, think about this as accelerators in general, but I'm narrowing in on some features of GPUs that create these particular problems. But yes.
Fully understood. Yeah, makes sense.
So working group, we discussed a billion options. I've apparently numbering hasn't worked, but we narrowed it down to 3 that were possible. I think we actually went through like 20 different options over time. I'm not going to expose you to all of those because a lot of them we threw out because they were just not going to work. They were wrong. I will mention the first option, which was, can we not just do this with a ready mode so that you guarantee that you always know that the buffers are set up? The problem is that there's no easy way to guarantee that the buffers are actually really set up in MPI. So let's just set that aside for now because we don't have a really good option for that without adding multiple new calls. The 2 options that we came up with that result in a single call are the following. pstart, which I'll cover in a bit, but it's a blocking start version that guarantees the buffers are negotiated. Or psync, which is an explicit call that's all it tells you to is that synchronizes buffers, but that wouldn't change. You'd still do an MPI start. You just potentially call psync afterwards. There's some interesting ramifications to pstart and how it would interact with start. So I will go through these, both pstart and psync next. So remember in our notes here that this is we need a solution, and this is a very key point. We need a solution that will work for the first iteration of a kernel launch, but also every subsequent iteration as well. So we had a lot of ideas about how you could potentially do these in inits and try to exchange this data. The problem with that is that you're not guaranteed that you have a buffer ready in each iteration of that start complete section of a persistent operation. So hence we've narrowed in on a pstart, something that modifies the start variable, or something immediately thereafter, which would be an explicit synchronization. So just remember that this is part of what's constraining us in solving this problem, is that we need it to work for the first iteration and every subsequent iteration. Because although you have the buffer set up, don't forget that when you come through the second time, you have to know that the other side is actually finished with the data in the buffer before you start writing all over it. So it's not buffer setup, it's more readiness to write to the buffer. So think about it that way. And I think you'll get the first iteration plus n iterations if you think about it as, may I write to my remote buffer, rather than do I know where it is and what to do with it. It's, do you have permission to write to that buffer remotely? So here's a pstart example. And I have used terms of blocking and non-blocking here for the purposes of common understanding of where we would stop and communicate. You can translate these into the semantic terms for local and non-local as well. I'm just using the most commonly used vernacular terms so we don't get into the semantics discussion on what I thought everybody on this call would be easiest to understand for everybody. So pstart, for instance, would exist as our existing operations. So typically you do a psend init, it's a local call. Now instead of doing pstart, which remember, start, which is a local call. MPI start is a local call, doesn't guarantee you that it's actually wiring up the buffers or anything. You can do stuff later on that at the original. This is a special pstart call. It blocks and it goes over and matches with a pstart on the receive side as well. So you have to wire up those two things. This introduces some interesting ordering, which is why this is the first example I'm showing you, but it's not necessarily the preferred example out of the working group. Then you go through and you do your p-readies, which are all non-blocking. That could happen on the device, for instance. Optionally, you could look at p-arrives for non-blocking. There are ways this could be done very lightweight on a GPU, but it's optional, and we don't have really good use cases for when people want to use the arrival, just because you can't do, it's not easy to do multiple iterations inside of a single kernel, for instance, because that requires you setting up commands in the GPU again. So what we want to actually do is sort of finish the kernel at this point between the waits, do an MPI wait, and then you'll see the iteration go again, where we do a pstart, you call your p-readies, and then you exit you do a pstart, start your kernel, do your p-readies, stop your kernel, do an MPI wait. I should mention that if folks are familiar with previous generations of GPUs, kernel launches are much cheaper now than they used to be with hardware. So launching and finishing kernels is not as much a concern as it used to be. Okay, so that's how pstart works. Go ahead.
Why does the no, you won't call, the call is blocking, I get it. But does the start on the sending side actually need to be blocking? I thought it's just the receive side you want to guarantee that the buffers are set up.
So you want to guarantee that the buffer that you're sending to is set up. That's what you want, right? Because you're doing a p-ready, which is a remote write. You need to know that the remote buffer is ready.
Okay, then the question the other way around, why is the p side on the receive side blocking?
That's a good question.
That is a good question.
But if you then how are you going to synchronize on one side?
Well, pstart would be
It doesn't need to be blocking.
Progress on the other side to eventually get into the init, and then it would
Okay.
release,
I
right?
Yeah, I see. Yes.
I assume P-start is still considered, local is the wrong word, but it's not a collective, right?
No.
It's still only one process involved.
Yeah, because this is point to point. Yes.
Right.
Yeah,
So
what's
perhaps you don't have to have a matching on the other side. It doesn't have to be, right?
no, what this is actually underneath the covers is the send side says I'm ready to send, RTS, and the receive side says you're clear to send. If the receive side gets to clear to send, it can just send that message, right? If you P started on the receive side, for instance, before the sender actually sent you a, hey, I'm waiting for you to tell me that your buffer's ready, you can always just send the clear to send from the receive side whenever you get there. And then the send side can actually observe that it already has permission to write to the buffer, that the buffer was already available on the other side. So there are side channel mechanisms that you can use to, this is really just an RTS-CTS handshake, right?
But would it be correct code if I do a start on the receive side instead of a P-start? Does it tend to be a correct code? Let me ask this way.
Well, let's put it this way. You wouldn't know on the first iteration, so we encountered this quite a bit. You wouldn't know on the first iteration through when you called MPI start that it was meant to be synchronized before launching anything, right? So
that's kind of what I'm shooting for. Then it becomes basically a collective operation. You have to have the P-start on both sides. One doesn't help, right? So now you're making a requirement that all processes in participating in that point-to-point communication have to call P-start. That's what I want to know if that's intended or not.
It is for that initial first operation. You're right that we had these discussions as well. The receive side doesn't necessarily have to do things. The problem is that it has to do it at least on that first iteration. And then it gets kind of weird when you want to put it in like a for loop that you have a special thing for the first time you did it, and then you do a for loop the future times with just start.
But then it becomes basically a special type of collective operation.
Yes.
It involves a group of processes.
Of n equals 2.
Yeah.
Yeah. And it can never be n more than equal to.
Sure.
Yes. Yeah. So from that perspective, the other things that we have from P-start are that because we're sort of creating a new type of starting, so you hit on this, Martin, right? Because you're creating a new type of starting now that is a collective start that's blocking, that requires the participation of both things. This can create some other issues too in semantic terms, because we're modifying what starting an operation means, and it opens up a bit of a hornet's nest.
Plus, you're introducing essentially a collective operation into a point-to-point initialization step.
Right.
Yeah, we're introducing that into the actual stages, right? Which we just discussed, which is why we didn't prefer P-start. There's some benefits to this next one that I'll show you, which is P-sync. It doesn't change that init start. Yes, you make one more call, right? But P-sync is optional, but it is, again, a two-way collective operation that's blocking. Now we can do some more interesting things with P-sync with regards to like a P-sync all type call, where you might synchronize with all of your senders, all of your remote buffers. For say a Halo exchange, you might synchronize with 4 adjacent remote buffers before you launch the kernel. That'd be fine too. They're really just RTS, CTS. There's nothing requiring ordering between these operations either. But P-sync pulls it out of that start operation. So it becomes much more obvious that this is optional, and you can do it wherever you want and whenever you want. So it's not, I want to start this communication again. I could synchronize. I could choose to not synchronize at some points in the future too. I don't have a lot of use cases for when you would choose that you would want to and when you wouldn't. It potentially, if you made a decision about whether you were going to farm it out to certain accelerators or not, or other accelerators through a kernel, there are performance portability libraries that may wish to make this decision, depending on which accelerator in a heterogeneous system they may want to farm things out to, or whether it's kept on the CPU itself. But psync is, again, a two-participant only collective operation that is synchronizing, that guarantees that the remote buffer is available. And then you do your p-readies, potentially your p-arrives, and you do a wait. But this, if you put a psync before kernel launches, would make the GPU optimization easy, makes GPU libraries trivial to implement for MPI, assuming you're only doing p-ready calls in it. But that lets us initiate communications from the GPU, and there are mechanisms that we're looking at with p-arrive to enable receiving information on a GPU for one round of communication. So it offloads all of the compute and communication initialization to the accelerator, but all of the setup and negotiation with the NIC and everything else that you do hardware-wise that GPUs are really bad at is all done on your CPU side in this model.
So you would pass the request object to the sync call? That the idea?
Yes.
Yes, next slide will show you that.
Yeah. So to show you that we prefer psync, I've drafted actual text. Now this is still rough text of, we have to go through this in the working group, so I don't want to represent this as a final work product, but we wanted to get this in front of people so we can start discussing it with the forum as a whole. And we may want to read what we have at that point at the next virtual meeting so people are aware of this. We can get some forward momentum on it as well. So the idea is that for MPI psync, you're passing in a request of type of a partitioned communication request, right? It's not valid to pass in other types of requests at this point. And then it basically just gives you back your request when it's done. It's just a block till you get your result back. So it says MPI psync synchronizes with the destination of a partition communication request, guaranteeing that the receive side buffer is ready to receive data. MPI psync is non-local and blocking. Partition communication request must be initialized, must not be inactive, e.g. MPI start must have called, and no calls to MPI p-ready must have been made after the call to MPI p-start. So you're fresh. You haven't actually done moving any data yet. If the user wishes to synchronize before beginning to call MPI p-ready calls, this call must be called by both the send side and receive side processes for a given partition communication operation. I should have put point to point in there. So I told you the text isn't finalized. Synchronizing prior to calling MPI p-ready is not required. And then we say advice to users, it may be beneficial to synchronize partition communications prior to beginning communication operations, particularly when using accelerators like GPU to call MPI p-ready. End of advice to users. And then I'll cover this real quick just because this is a follow-on. You have a sync all account call as well, where you can feed in an array of requests, which we say is like calling MPI psync in some arbitrary order, but because they're collective operations and we've technically said it's blocking, I added in here that as MPI psync is non-local and blocking, the order in which the operations is performed in the MPI library will not cause deadlock due to operation ordering. Really what's actually going on underneath the covers here is a literal ping the other side, hey, let me know when you're ready to send. The other side sending you back a clear to send. There's no operation ordering that would prevent you from communicating and doing essentially n equals 2 collect number of participant collectives, n equals count, and having them block in any way. Sync all is just a nice utility to be able to synchronize in all of your remote buffers at once. That's the goal there, but there'll be some wordsmithing that we'll have to do with that. So I'll go back to psync because it covers more of the concepts, but
thoughts? Slide back.
Sorry, how many slides, Martin?
Just one back.
Yep.
I don't know if else, I think I interrupted someone else, but hopefully they can speak next. What is the difference of this code to whether I would, let me see if I get this straight now, do a send after the start on the receive side and a receive on the send side before the start? Isn't that equivalent?
Ah, yes. So you hit
Yes.
on one of our other slides. Yeah, yes, it should, but this is the trick where we get back to the point at which I made with ready mode, that if you've done a send and receive, right, that doesn't guarantee you necessarily. It guarantees you that the operation has been started on both sides, right? AKA MPI start and MPI start have all been called, right? The problem is that MPI start just guarantees you that you can start the operation. It doesn't guarantee that both buffers, the actual buffers that you can write into from a hardware perspective, are ready. It just guarantees you that you can accept those calls into MPI, which could be a buffered case depending on your implementation. So if you do a send receive, it may be implementation dependent on whether your buffers actually exists and is there and is ready to write to.
But isn't that the same? So in your case, that's not listed in the document either, right? Because that's an internal to MPI, whether the buffer is really ready to receive a message. What does it mean a buffer ready from a user point of view?
So this is the trick for the optimization, right? So in typical MPI, you don't care, right? What does it mean whether the hardware is actually ready to do it or not? The library is ready to accept the buffer, and therefore you can hand it over and you don't care what's happening in the hardware, right? This is a weird optimization path where you actually do care. You want the library to never do any buffering for these particular calls in this situation ever. And so you actually need to guarantee that for this optimization, that the hardware buffer itself is available and the memory is free to be written to on the remote side, such that you never have to keep local copies or you never have to delay an operation because the remote buffer is available or not. This is one case where the user actually cares whether the hardware on the other side is actually ready, because it lets you create a much more optimized send on your hardware when you know that is the case.
Ryan, can I put something in here if you'll allow it? There are other approaches that we've been discussing too, and I'm not trying to distract from your approach, but for example, we could say there's an R, this is like an R send. But we wanted to have an R send or like an S send analogy, but with a full channel now, not just a send in it and a receive in it that can match anything. So because they match each other once, and so there's an analogy here to RSend. We want to make sure it's correct. We don't want to pay for things we don't need to pay for. We've elected essentially to put the logic of RSend and SSend into an extra call stage, as another stage in the semantics to ensure optimization. There are other ways we could go too, and the forum might suggest some of those, but this is the best way we've come up with so far. So I just wanted to put a plug for it. We're thinking carefully about how the stages of progress in the protocol actually, just like an SSend and RSend, are revealed to the user. And here we think a call helps us to make that as optimal as possible. You could have an RSend mode where you know that synchronization has happened through other information. It's still clearer for the user to specify it. So I just want to point out we bandied around a bunch of options, and this is the best one we've come up with so far. So that's my advertisement. Please go ahead, Brian. Sorry for interrupting you.
Oh, no, yeah, I think that's a really good point, Tony, that we have investigated. Can you do this as the synchronous send doesn't really work because the synchronous send only guarantees that the buffers are, that the data has been accepted at the remote side during the wait. It only guarantees it at this completion stage. So we didn't think that completely worked. And then the ready mode solution for a ready mode in it, it may be possible to know that remote buffer is available, but we don't know exactly how it's possible to know that remote buffer is available. This is a trick with MPI, right? Of the fact that MPI doesn't, a very good thing, MPI doesn't expose you to all the little tiny internals and details of exactly what's going on with memory buffers. This is a unique case where we've seen that you really need to know that. And that's because, GPUs don't do MPI well. So this is a case of trying to avoid doing anything really normally MPI centric on the GPU while still providing MPI communication semantics and all the guarantees and everything else that goes along with MPI by supporting that from the CPU. But we're very much open to participation, new suggestions, this sort of stuff. This is the best thing that we've come up with after many hours of conversation.
By the way, we did discuss whether it should be just sync without the P, and could that be used to actually guarantee that the ready mode is, ready to work. So, of course, somebody could say, hey, why just limit it to partition communication? Why don't we make it just a regular sync function so that we can now use that to say that, hey, if you used a ready mode, send, then we can guarantee that the actual receive is posted on the other side. So,
but it would
there is a
require the
possibility
assertions on the communicator for you. It does require for that to be meaningful. The assertions on the communicator, there's no any wildcard, no any send.
Yes,
As
yes.
long as those assertions are present, then that sync call would make sense. I don't want to put for communicators that have limited themselves with those assertions. Yes, we believe that.
Yes, the psync is targeting partition communication because it has the matching semantics all already there, and it has certain requirements with regards to no wildcards that make this a lot easier to specify without running into corner cases. So the reason that we're not proposing a general sync call is that the corner case discussion exploded on that one.
Exactly. So in fact, I was a big proponent of just going with the ready send. And when I looked at all the possibilities and when, Brian and Tony got into these details, I said, no, let's keep it p-sync because we just can't solve all the problems.
I'm still not fully understanding why the send receive wouldn't work. And I don't see the difference to this solution. So if you do the send, what is after the start and the receive before the start on the send side, I realized that the semantics of start, the way we have an MPI does not guarantee that the stuff is actually started. It just initiates the starting part, right? The implementation could decide to do that. The implementation could say, if we call start on a receive, I make the buffers immediately available. That's an implementation choice. The same way here, an implementation could decide on a p-sync to do nothing. That's still a valid implementation. Then it has to do all the checking in the receive and the arrived and the p-readies and so on. But the fact that you use the buffers is an optimization in the implementation. P-sync for the user doesn't do anything actually from the user semantics, right?
From the user's point of view, it doesn't really guarantee them anything. It just tells them what the performance of a p-ready will be because it takes a single path through the code. So you can determine ahead of time what your p-ready is going to do in terms of its overall performance and its behavior.
So
I would point out that I agree. You could decide that an MPI start and an implementation actually does stuff, right? It is defined, though. The MPI start is defined as local. So you can't guarantee. So I actually proposed this exact same thing first. And then we had a very long conversation on this. I agree that the issue comes down to the fact that you're not guaranteed that the send receive means that the start has actually negotiated anything, because it could just be entirely local. And so what that means to you is that if you just say, well, your implementation may implement start correctly, may implement start so that it can perform this optimization, the GPU side implementation of MPI, because remember, you're actually going to have a different binary for implementing that MPI call on the GPU than you would on the CPU side. That binary on the GPU then needs to know either needs to be provided by the MPI library itself, so the GPU vendors aren't providing it, or the GPU vendors need to deal with every single implementation that could pass it information, which will then they'll have to determine whether or not they support that particular MPI implementation.
Well, yes and no, right? You still have to have the P-ready run on the GPU. So the P-ready has to be implemented by the GPU. Vendor, MPI, implement whatever, but somebody has to implement that, and it has to match what you do in start. If you get an optimized start, you can make a simple P-ready. If you're lazy at start, you have to make a complicated P-ready.
Correct. And the that introduces the extra if statement, and it also introduces the complex P-ready. And the complex P-ready, I originally thought this wouldn't be a problem either. The complex P-ready performance may be underwhelming.
Yeah, but that's up to the implementation. If the implementation does the optimized start, you never have to have the complicated P-ready in your implementation. You just have to have the simple one. You just have to be consistent within your own implementation.
Sure, the problem is that you can't necessarily guarantee in an implementation that the start has always provided the optimized version because of the fact that it's defined as local and non-blocking.
Yeah, that's fine. It's still weak local, right? So you could still do the whole handshake with the other side. That's totally allowed in a start.
Can you actually, though?
That's what I thought we decided in the terms discussion, that every single MPI routine could communicate as long as it doesn't require a particular routine on the other side.
There could be communication in the background.
I think we even said something like comrank could technically be communicating.
It can technically communicate. You're just not guaranteed when that communication, what you're trying to do with that communication is actually completed, right?
The start wouldn't return until this is done, which is not considered blocking based on our new terms and conventions. I'm channeling my inner wolf now. I hope that comes across.
Yeah, don't get me wrong. If we can actually provide a guarantee that start could do that, that would be fine. Because you could guarantee that between your.
But even if you do that, what about the second iteration?
Well, the start would still be blocking, right? It would still be an RTS, CTS.
Okay, so it would be the same thing next go around too.
It would be the same thing next go around. As long as that's actually guaranteed, we can actually do that and guarantee that that's true every single time you run the start. Then I agree that you don't need the p-sync. The debate here is whether or not you can guarantee that in a start.
I think it's not guaranteed to the user, but an MPI implementation internally can guarantee it to itself, I think. That's at least my understanding of the new blocking definition. The local definition.
Yeah, the weak local.
It's all weak local, right? Yeah.
Okay, so this seems like a really good thing to discuss with the larger forum as well. If we put together a reading for p-sync for the next meeting, and we'll discuss these issues again sort of off of that, and the forum says, you don't need to do p-sync because we understand that start does this for us. I think we're also good. That's great. We did it right the first time then.
I mean, what I could see is a new start that also takes an info object, like a start with info, that you could then change to modify the behavior of start and say, I always wanted return immediately, whereas I wanted always to wait until it has the handshake on, right? For optimization point of view, but the standard start could just do what you want.
Yeah, I think you probably want the implementation when you're doing the start for this type of operation to have some sort of maybe it's info communicator that you're using for it, for instance, such that you know that it's guaranteed always true or not true, such that you could actually run the right p-ready with that type of start, just so that you always know that you're guaranteed to get that behavior. The goal here is just simply to get the same behavior with regards to buffer readiness every single time you run this. The goal is just consistency.
At least it should be at the init call, maybe even the communicator, yeah.
Yeah, something on that level, just as long as we, either we don't agree that start can or can't do that, and we need a new call, or we all agree that start can do that, and maybe then at that point I'll propose some non-normative text as like an advice to implementers or something, advice to implementers and advice to users about start. Telling people the forum determined that you're allowed to do this. So implementers, you can go ahead and implement your MPI library on like a GPU with a p-ready with these assumptions, and your implementation should be able to do this and guarantee this all the time. That may be a good solution too.
Sweet.
I have a bit more general question around this, especially on the one-sided people here. Because for me, this looks like you are really interested in this buffer and if it's available or not. And I see a bit of a parallel way here to like initializing a window, which is shared between the processes, and then having a fence. So could you implement this on one-sided as well as an alternative?
Could you implement it with one-sided?
Yeah. With existing one-sided semantics.
So with one-sided semantics, you could potentially do this as well. Underneath the covers, realistically, with hardware, how you're really going to do this in practice is with RDMA operations for each of the individual partitions. That's probably the most efficient way to implement it. Doing it with MPI RMA is a little bit trickier, though, because you can, active target that wouldn't work particularly well on a GPU. There's more complication with the RMA side. But yeah, what partition communication has been giving you from the beginning is the ability to move data around like you can move around data with one-sided, with more structure and completion notification built in without synchronizing the window, right? So partition communication does have a lot of parallels with one-sided communication. The goal of it was to try to pick the best stuff out of the two-sided model that made it easy to work with, and the best stuff out of the one-sided model that made it highly concurrent, and jam those two things together to give a model that gave really good matching semantics so that you could understand what was going on, while at the same time allowing you to do a lot of the stuff that you could do for optimizations with one-sided code. So yeah, there's always these parallels here. Now, are you proposing that you want to like do one-sided for this type of GPU communication?
Yeah, I was thinking often like because you have you have also shared memory between the GPU and the CPU, so
you could potentially.
I'm not a specialist in GPU programming, but I just
The trick with the one-sided and puts, if we get into the technicalities of it, is that when you want to do a put off of the GPU for MPI at least, you still have to look through a variety of data structures and initialize the commands. It's not the worst thing in the world, don't get me wrong. It's certainly better than doing an MPI send from a GPU. But having all the communication set up on the by the CPU is going to be faster than setting up communication by a GPU. So supporting those models is another way to program GPUs. But you'll probably notice that when you go to the larger events and people sit in the audience and complain about being able to use MPI with GPUs, they're not saying they're okay with the one-sided model as it exists.
So the other issue when we were playing with the same stuff, and we tried this with RMA. The other RMA issue is that RMA is not really intended for point-to-point because you have a window, the window is a communicator, and synchronization
Yeah,
is somehow
yeah.
always tied to the window. So you would have to basically create sub-communicators for every point-to-point that you have.
Mm-hmm.
Yeah, that's a lot of overhead. But
Yeah.
So I think if you wanted to go this way, this maybe in addition to that, or a separate proposal, I think maybe we have orthogonal, you would have to kind of have a point RMA synchronization. That may work then somehow, I think, with all the caveats that Brian just pointed out.
But you know, conceptually, you could say that the p-sync is sort of like a fence, but obviously, you know, they are on two different sides.
Yeah.
yeah, and the one is for two communication partners, and the other is open for how many you want to use.
Exactly.
Like I said, this is really just trying to constrain the space so that you can do the right thing on your accelerator, so you don't have a lot of options, so that you can get the optimal performance out of them. So yes, it is going to be subsets of other stuff that we can do, but it's a purposeful subset. It's pushing us in a direction there. And of course, partition communication as it exists now in the standard is not this tight subset necessarily, right? So you do have more flexibility if devices change in the future and whatnot. But for devices that do have these limitations, and we probably will still have these limitations on data flow centric devices for the very long future, this sort of constrains the problem and makes it easier for them to really be optimized in terms of communication. And we can finally get people off our backs complaining the MPI doesn't care about GPUs.
The GPU part, the one thing is that we kind of went a little bit in the beginning with the process, right? And then you said, like, how do you match this? I'm still not quite clear who would implement the MPI ready, the P ready, and how you would link this all together and ensure that you have a consistent program.
Okay, so this particular model here, right?
Yeah, I mean, this could be an AMD, an Intel, or an NVIDIA GPU. But it's the same, but you have a different host. So the combinations of GPU, MPI, and host MPI could be huge, right? And how do you manage this without having the graphic card vendors have to supply something for every single MPI? You have to provide for every single GPU type.
Yeah, so fundamentally, if I had to create this today, the GPU vendors will have to support different networks available, right? If they wrote an MPI ready. What's actually going to happen with these is just basically that's just the mechanism that they use to ring the doorbell. Doorbells are different, the counters are different, the triggering mechanisms are different between the different networks. But fundamentally, the CPU side in the MPI implementation is still handling all the communication setup and the completions. So all this is really doing is just ringing a doorbell or incrementing a counter or doing something on that side. So GPU vendors don't really actually have too much to write. It's literally, how do I ping that individual device? Which device do I have and how do I ping it? And then the rest of the internals of how MPI hands stuff over, sure, you'd have to discuss exactly how MPI hands to the device the information about where those doorbells are or where those triggers are, but I don't think it's too difficult for them to support MPIs because this is brand new, fresh stuff. So the GPU vendors, I would expect, would have to be involved in that, or the MPI implementers will do it.
So I see it this way. So for example, there's a certain network vendor certainly contributes even to open source MPIs, whether it's a transport layer or verbs or what have you. And now what you say with an assertion and a communicator, this assertion and info key, there are no info key right now on the send in it and receive in it for partition. We might make a new version with info in MPI 4.1 if we decide it has to be there. Otherwise, on the communicator, simply then you have a derivative if you're making your own commercial MPI or you're using a derivative of Open MPI, which is often the case. You make an assertion. That assertion means that when you implement p-ready, p-sync, you know you're dealing with GPU offload. And that's so these things don't change the rest of the standard. They're very narrow. They do involve some annotation or an info key or an assertion, an info key that's an assertion, effectively. And it's already going on behind the scenes that vendors of specific high performance hardware are either informing free software or building derivatives of free software in order to achieve their deployment. So it doesn't really change anything. It's just like a little bit more logic in the transport, and it's a sidebar to what we already do.
I will mention that making these guarantees actually makes the implementation of p-ready much, much, much more simple and easy for each device. So I would anticipate that the GPU vendors will be able to support the full environment much easier when they know that they basically just have to ring a doorbell.
Sure, that all makes sense. It's really just a matter. It's more again an engineering question, right? And how to get this fully. Another option would be to talk with the OpenMP folks and see if they for their target stuff, which would be again a separate thing, could provide a general doorbell mechanism that we then could pick up and layer on our side, and it would be standardized on the other side. We wouldn't. And
so Martin, we're looking for things that have O of 1 instruction effects in these kind of operations. We're not looking to have super general semantics. We're just saying that the implementations can see their way to very cheap implementations that are very, very fine grained. So O of 1 instruction effects everywhere. Sure. So although some kind of, in order to be cheaper or more portable implementation of MPI, you might choose this layering stuff. It's inimical to this idea of ultimate performance for exascale. So I want to make sure we don't go down some path that we have to, in order to get this to work, you have to call some third product or things like that that are heavier than a handful of instructions.
That's clear. That's clear. A doorbell has to be a doorbell that is just a flag, right?
Yeah, the nice thing about this is that you don't actually have to have a communication path back out of the kernel. It's literally a one-way path, right? As you call the p-readies, the devices themselves will complete the operations, and those completions will exist in hardware queues that you observe in MPI wait back on the host. So the host is able to just basically pass some information about go ring these doorbells. They all get rung, and there's no communication that has to come back software-wise from the GPU kernel. That communication can happen through the hardware devices themselves. So, and that should be true for every single network that I'm aware exists. I can't think of a network where that is not the case, but somebody may be able to prove me wrong with a crazy network I'm not thinking of.
We'll find one.
There's always one.
Exactly. Okay, any other questions or comments on this? If not, you took us right to the end of the meeting. Congratulations.
There you go, Martin. Always feel it's like gas, right? We expand to fit the size.
Seems like it. No, but we should definitely have time in the August meeting to discuss this if you're ready at this point. So if you want to call it a reading or if you want to just call it a feedback session, doesn't really matter. Just let me know and we can put it on the agenda.
I think we're pretty close on the text. Like I said, we got some touch-ups we need to do with the group, but I'll try to get that done this week so we can have a reading of it and have more discussion. Maybe we decide we don't need it at all and Start does it. Great, but we'd love that feedback sooner rather than later. So I'll put something together. And
so Ryan, if you need to do an official reading, then Monday would be the date we have to send it out. So
I know we need to discuss this and finalize the text this week, at least for our that exists right now.
I would like to recommend that you go for that goal because I think we could start reading things for 4.1 from our working group. Possible to start pipelining it into the next versions of MPI. So I'm going to, as the working group chair, think that's a great idea to try to get a reading sooner rather than later because I think you're very close.
Just a couple minor typos in the ticket, but I'll finalize that and we'll have to put together an official ticket, but the text is all there. So we'll get this covered and hopefully, well, we will definitely have a reading next meeting. So thanks, Martin.
Right. Any other last items then for today?
I've got a question for you, Martin. Maybe I already asked it, so if I did, I'm sorry. While we were working on the ComSplit type, the new type values, we found that the text for the actual text for ComSplit type was not very good, and we wanted to improve it. So what would be the best course of action here? Should I already drafted some text. I already have some text that is not completely ready, but that is in good shape. So should I try an errata for this?
Does it change the meaning?
No, it's we reformulate the text because the text is not very clear and some words are not the right one, and so that's it doesn't change the functionality. It's just a rewording, words missing, I would say.
So I would suggest, yeah, I would announce it as an errata, and then we can discuss in the August meeting what folks want to do with it, if it's a full or if it's an editor change or what we want to be. But if you put it on as an errata reading, at least it's on the official agenda, and then we can do whatever we want with it.
Okay, so I should do that before Monday, right?
Yes, please.
Okay, good. I'll do that then.
Perfect, thanks. All right, I think that gets us really to the end. Perfectly 7 o'clock here in Germany. Have a good evening, good day, wherever you are. For some of you, I think also good night. And talk to you. We'll see if we need a meeting next week. We'll send email out for that in case we still talk to each other on the August meeting. Thanks, everybody.
Thank you, everyone. Bye.
Bye-bye.
Thank you. Bye.
Bye.
Bye-bye.
Bye.